Welcome. We're diving into brain-computer interfaces today and how researchers are finding new ways to make them even better.
And a particularly exciting area is how we can make these interfaces more effective for people who have difficulty with movement.
So for anyone who might not be familiar with them, a brain-computer interface, or BCI, basically creates a way for the brain to talk to an external device.
That's right. And this tech has the potential to do so much. Things like controlling prosthetic limbs or navigating virtual environments.
It all sounds pretty incredible.
It is. And a key part of this is something called motor imagery, or MI. This is where users imagine a movement, and the BCI system decodes these brain signals to control the device.
So you're basically thinking about moving, and the machine responds. That's pretty amazing when you think about it.
It is, but there's a catch. MI has huge potential for things like rehabilitation, but it's not always easy for people to do well.
I see. So it's not as simple as just thinking about moving your hand, and it happens.
Unfortunately not. Studies have shown that around 15 to 30% of people struggle with MI, which makes DCIs less effective for them.
So there's a portion of the population that can't really benefit from this technology.
You could say that, and that's sometimes referred to as BCI illiteracy.
BCI illiteracy?
Yes.
So researchers are always looking for ways to help people get better at MI. And that leads us to the focus of today's deep dive. We'll be exploring the somewhat surprising connection between something called the rubber hand illusion, or RHI, and its potential to actually improve motor imagery.
It might sound unbelievable, but the RHI is a well-established illusion in neuroscience that really shows how adaptable the human brain is.
So how does this illusion work?
Well, researchers can trick the brain into thinking a rubber hand is part of the user's own body, just by synchronizing what the person sees with what they feel.
I'm having trouble picturing that.
Yeah.
So let's say I'm participating in one of these studies. Would there be a rubber hand in front of me?
Yes. You would see a rubber hand placed before you while your real hand is hidden.
Okay. And then?
Both the rubber hand and your real hand would be stroked at the same time. And as your brain experiences this, it starts to believe that the rubber hand is actually yours.
It's like the brain is being convinced to accept this external object as part of its own body.
It really is. It demonstrates how amazingly the brain can adapt and change how it perceives the body based on the sensory input it receives.
And there's actually growing research that suggests there's a connection between this RHI and MI.
That's right. There seems to be some overlap in the neural mechanisms behind them.
So that connection suggests that inducing the RHI might actually be able to make a person better at motor imagery. And the researchers we're focusing on today really explored this connection.
They did. Their study looked at how different ways of inducing the RHI in a virtual reality setting could improve motor imagery performance.
So they're using VR to create this illusion.
Exactly. And they went beyond just measuring classification accuracy, which basically means how well the BCI can figure out what movement the user is trying to make.
I can see how just looking at classification accuracy might not tell the whole story. What other things did they measure?
Well, they looked at brainwave patterns in more detail, specifically something called Erter's amplitude and differentiation.
Can you explain what those are?
Sure. They give us a deeper understanding of how the brain responds during motor imagery.
And they also got feedback from the participants themselves.
That's right. They wanted to understand how strongly the participants felt a sense of ownership over that virtual hand, since this can affect how well the illusion works.
It sounds like they took a pretty thorough approach, considering both what was happening in the brain and what the participants were experiencing.
Definitely. They really aimed to get a complete picture of how the rubber hand illusion affects both the brain and the person's perception.
Now, before we get into the details of those 5 RHI induction methods, can we just make sure everyone's on the same page?
Of course. Clarity is key.
Okay, so just to recap, we're exploring how the rubber hand illusion might hold the key to improving brain-computer interface control, especially for those who have trouble with motor imagery.
Right.
The researchers we're discussing today wanted to examine 5 different ways to create this illusion using virtual reality.
That's right.
And they used brainwave patterns and feedback from the participants to see how well these methods worked. Now, are you ready to walk us through those 5 methods?
Yes, I'm happy to elaborate.
Great. I'm sure everyone's eager to hear about them.
So we've laid the groundwork, understanding what the researchers were hoping to achieve and how they went about it. Now let's get into the specifics of those 5 methods they used to induce the RHI.
Okay, I'm ready. I find it fascinating that they can actually create this perceptual illusion. So tell me more about how they did that.
Well, the first method is called active movement, or AM for short. In this method, the participant actively moves their hand, and they see a virtual hand in the VR environment copying those movements.
So they see their own hand moving, but it's a virtual version.
Exactly. And that synchronous movement helps create a sense of agency, that feeling that they are in control of the virtual hand's actions.
So it's like the brain is thinking, if I'm the one moving it, it must be part of me.
That's the idea. And that feeling of control, of embodying the virtual hand, could be really important in enhancing motor imagery.
Okay, I see. That makes sense. So what's the second method?
The second method is called haptic stimulation, or HS. In this one, an object touches the participant's real hand, and at the same time, a virtual object touches the virtual hand in the VR environment.
Well, now we're adding a sense of touch to the illusion.
Right. That simultaneous touch creates a synchronized tactile experience.
So it's more than just seeing it. Now they're feeling it too.
Exactly. And this method has been shown to be very effective in inducing the RHI, leading people to feel that the virtual hand is actually part of their body.
So the brain puts the visual and tactile information together.
Yes.
Okay. What about the third method? Does it build on these first two?
Yes. In a way, it does. It's called active movement plus haptic stimulation, or AM plus HS. Here, the participant moves their hand to touch an object, and at the same time, they see and feel that same interaction happening with the virtual hand.
So it's like a combination of seeing the movement and feeling the touch at the same time.
You got it. And this hybrid approach is based on the idea that combining active movement with haptic stimulation might create an even stronger RHI, which could mean even bigger benefits for motor imagery. We'll talk about those results a little later, but it's a really interesting idea.
Yeah, so we've got three methods now. Two that are more active, and then this hybrid one. Now, are the other two methods also active?
Not quite. The fourth method brings in something a little different. It's called passive movement, or PM. And in this one, the experimenter actually moves the participant's hand, and the virtual hand in the VR environment follows along.
Okay, so the participant isn't the one initiating the movement this time.
That's right. This one is particularly interesting because it could have implications for people with severe motor impairments who might not be able to actively move their limbs.
So you're exploring whether a more passive form of this illusion can still affect motor imagery.
Yes. And that's really important because it opens up the possibility of using this research to help a wider range of people.
That makes sense.
Okay.
So what about that last method?
The fifth and final method is also a hybrid, kind of like AM plus HS, but this one uses passive movement. It's called passive movement and haptic stimulation, or PM plus HS. So you've got passive movement done by the experimenter, combined with that synchronized tactile experience of haptic stimulation in the VR environment.
So we've gone through a whole range of methods, some fully active, so entirely passive, and some that combine the two. It's a pretty comprehensive look at how different types of sensory input could contribute to this illusion.
It is. Those 5 methods provide a solid framework for investigating the different aspects of RHI induction and how it might impact motor imagery. But before we dive into the results, let's make sure we understand how they actually measured the effectiveness of these methods.
Yes, you mentioned earlier that they went beyond just measuring classification accuracy. Can you talk about those other measures a little more?
Absolutely. They dug into the details of what was going on in the brain's electrical activity, specifically by looking at 2 key things: errors, amplitude, and differentiation.
Those terms sound a little complicated. Is there a way you could break them down for us?
Sure. Imagine you're looking at a fingerprint. Everyone's fingerprint has a unique pattern of ridges and valleys that makes it different from everyone else's. Our brains work in a similar way. They generate specific patterns of electrical activity when we do different mental tasks.
So you're saying that brainwave patterns are like unique signatures of what our minds are doing?
Exactly. Now let's apply this to motor imagery. When someone imagines moving their hand, specific changes happen in those brainwave patterns. And these changes are often called ERD, which stands for event-related desynchronization, and ERS, which means event-related synchronization. They're basically fluctuations in how strong certain brainwave frequencies are.
So ERD means those brainwaves are getting weaker, and ERS means they're getting stronger.
That's a good way to think about it. So the researchers wanted to see how the strength or amplitude of those ERDRS patterns was affected by these different RHI methods.
So if the RHI is making motor imagery better, we would expect to see bigger changes in those patterns.
Exactly. If the ERDRS amplitudes are stronger, it means there's a more robust neural response during motor imagery, and that could lead to better control of the BCI.
What about differentiation? You said that was another important measure.
Right. Differentiation looks at how different the brainwave patterns are when someone imagines moving their left hand versus their right hand. Think about our fingerprint analogy again. It would be hard to tell the difference between two fingerprints that look very similar.
I can see how that would be tricky.
And in motor imagery, a higher degree of differentiation means that the brain signals for each hand are more easily distinguishable.
Which I guess the BCI system needs to work properly.
Yes. It needs clear signals to understand what the user wants to do.
So if the signals for left and right hand imagery are all mixed up, the BCI might get confused.
That's right. It might misinterpret the commands.
So you've got these objective measures of what's happening in the brain, but you also mentioned that the researchers got feedback from the participants.
Yes. They wanted to understand how strongly the participants were experiencing the illusion, specifically that feeling of ownership over the virtual hand.
Because even if the brainwave patterns look good, it's important to know what the participant is actually feeling.
Exactly. They wanted to know whether the participants really felt like that virtual hand was part of their own body, because that sense of embodiment can really affect how well the illusion works.
It sounds like they were taking a very well-rounded approach, looking at both the brain data and the person's experience.
They were. They wanted to get the most complete picture of how this rubber hand illusion affects both the brain and the mind.
So I think everyone is waiting to hear about those results. Did those RHI methods actually work?
The results were pretty exciting, especially for the first three methods we discussed, the ones that used active movement, haptic stimulation, and passive movement.
The ones that went from completely active to completely passive.
Yes, and all three of them resulted in increases in both Erder's amplitude and differentiation compared to the control group.
And the control group, they didn't experience the illusion, right?
Exactly. They were just given visual guidance. So the fact that all three methods led to improvements in those brainwave measures suggests that the illusion itself is really having an impact on motor imagery.
So even just tricking the brain into thinking that rubber hand is its own is enough to change the brain's motor signals, even when they're just imagining movements.
It's pretty amazing when you think about it. And remember, we're not just talking about whether the BCI could understand the movements. These findings suggest that there's more activity going on in the brain areas related to movement, a more distinct signature of that motor imagery. And that could have a big impact on how well someone can control a BCI.
It's almost like the illusion is strengthening those brain pathways, making the signals clearer for the BCI to pick up.
That's a great way to put it. Now, before we move on to the results of the hybrid methods, I'm curious, based on what we've discussed so far, do you think those three traditional methods might have worked differently?
Well, we talked about how important that sense of agency and embodiment is. So I would guess that the active methods, AM and HS, might have had a bigger impact than the passive one, PM.
That's a really good observation. And you're right, AM and HS, the ones where the participant is actively involved, did show greater improvements compared to PM.
So it seems that actively participating in the illusion might be more effective than just passively experiencing it.
Precisely. That sense of control of actually being the one to move that virtual hand seems to be a key part of why it works so well. It reinforces the idea that our brains are more receptive to change when they feel like they're the ones initiating that change.
It makes you wonder if maybe just watching an illusion happen wouldn't be as effective as actively taking part in it.
That's an interesting thought. So let's move on to the results of the hybrid methods, AM plus HS and PM plus HS. Those combined elements of both active and passive participation along with the haptic stimulation. I bet you're wondering how they performed.
I am. So did those hybrid methods live up to the hype?
Well, the findings were definitely interesting. AM plus HS, the one that combined active movement with haptic stimulation, was the clear winner. It produced the biggest improvements in Erder's amplitude differentiation and even those subjective ownership scores.
So engaging multiple senses at once and having the user actively participate really seems to create the strongest illusion, leading to the most improvement in motor imagery.
It does seem that way. The findings suggest that this multisensory active approach creates a sort of supercharged RHI, really maximizing the benefits from motor imagery.
This is really exciting. It could have a huge impact on developing new and more effective ways to help people control BCIs, especially those who have difficulty with motor imagery.
It could. But it's important to remember that every study has its limitations.
Of course.
And the researchers did point out some limitations in their methods, particularly with how they controlled some of the stimuli. They had to do some things manually rather than using more precise systems.
I can see how that might have affected things.
Yes, and they suggested that future research could use things like robotic arms to make sure the delivery of haptic stimulation and passive movement is more consistent and controlled.
That's a good point. And I'm sure they also suggested doing more research to see how long these effects last.
They did. It's important to know if the benefits persist over time and if they actually lead to real improvements in BCI control in the long run. Those are questions for future studies.
Definitely. Now, even though AM plus HS was clearly the most effective overall, I'm particularly interested in that PM method, the passive one, especially for individuals with severe motor impairments. Did the researchers have any thoughts on how that method could be improved for those individuals?
They did. They think that PM, even though it didn't perform as well overall, could still be very helpful for people with limited mobility. And they suggested that adjusting the speed of the passive movement in PM, making it more personalized to the individual's needs, could make it more effective.
That makes sense. It highlights how important it is to tailor the BCI experience to each person.
It does. And there are other ways to personalize it, too. Remember our discussion about multisensory experiences. The researchers suggested that creating VR environments that are more personalized to the individual's preferences and interests could also boost the effectiveness of this type of training.
So creating virtual worlds that not only create the illusion, but are also engaging and meaningful to the individual, that's a fascinating idea.
It is. And it could really change how we approach rehabilitation in the future.
We really are only just scratching the surface of what's possible when it comes to using the brain's amazing adaptability to improve BCI control. This research really shows how creative scientists are in pushing the boundaries of what we thought was possible.
I agree.
It's an exciting time to be following these advancements. Who knows what incredible breakthroughs are just around the corner. But for now, we've reached the end of part 2 of our exploration into the connection between the rubber hand illusion and motor imagery. Let's take a short break and come back for part 3, where we'll wrap up our discussion. Welcome back. We've been exploring the rubber hand illusion and motor imagery, and we've seen that inducing the RHI can really enhance a person's ability to perform motor imagery, which in turn can lead to better BCI control.
And what's particularly interesting is that this research doesn't just demonstrate that the illusion works. It goes a step further and really investigates different methods of induction. And it highlights the importance of active participation, multisensory engagement, and personalized approaches.
I agree. It's exciting to think about the implications this research could have for BCI technology, particularly for rehabilitation.
It is exciting. Imagine a world where individuals with motor impairments can regain lost function or even control assistive devices more easily and accurately.
It's a hopeful and inspiring thought. Before we wrap up, I'd like to touch on the broader significance of this research. What does it tell us about how adaptable the brain really is?
What I find so fascinating is how this research really showcases the brain's plasticity, its ability to actually rewire itself based on sensory experiences. The rubber hand illusion is essentially a form of sensory re-education, tricking the brain into accepting this foreign object as part of its own body.
And by doing that, we're essentially harnessing the brain's natural ability to change, creating new possibilities for improving motor imagery and, in turn, BCI control.
This research really opens up exciting new avenues for using sensory illusions as therapeutic tools. It challenges us to think outside the box when it comes to rehabilitation, to find innovative ways to tap into the brain's extraordinary ability to learn and adapt.
It's a great reminder that the brain isn't fixed. It's dynamic, constantly changing and evolving based on our experiences. And as we learn more about the brain, who knows what other amazing discoveries we'll make.
The possibilities are endless. This research really exemplifies human ingenuity and our unwavering commitment to understanding the intricacies of the brain. It pushes us to continue pushing the boundaries of what's possible, to explore new ways to connect the mind and machine, and to unlock the full potential of what humans can achieve.
It's inspiring, to say the least. And with that, we've come to the end of our deep dive into the rubber hand illusion and its potential to revolutionize motor imagery and BCI control. We hope you've enjoyed this exploration and that it sparked your curiosity about the incredible capabilities of the human brain.
We hope you continue to explore, to question, and to delve deep into the vast world of knowledge.
And remember, the most groundbreaking discoveries often come from the most unexpected places, just waiting to be unearthed by a curious mind.